Um, Welcome back to another video. Now, this video is about atmospheric pressure. In the last video, we talked about the pressure in a liquid, the pressure in the water, and we said that as we go deeper under the water, the pressure increases because there's a more and more layers of water which are pressing down on us. Therefore, the pressure is greater. Well, the atmospheric pressure is very similar. If you can imagine that we live under a sea of air, okay, which is our atmosphere, now, which is a layer of gases, okay, the atmosphere, and that's also exerting pressure on us. It's the weight of the air that exerts pressure on us. And this weight depends uh, on the height above the ground. Like for example, if you're at the sea level, okay, there's this much layer of air that is pressing down on you. So this height, that much layer which is pressing down on you. Now, if you're on top of Mount Everest, okay, there's only this much air pressing down on you. Okay, so the height is less. So therefore, the pressure here will be less. So as we know that as we go higher up in the mountain, the pressure decreases, and people get all sorts of effects like nosebleeds and things because of that. So the pressure increases with depth, and it's due to the weight of the air that's acting on us. Now, we can show this by a very simple experiment. If we do this crushing can experiment, now, if you take an oil can, which you can buy from the shop, you know, the gallon can, and you take all the air out of the can, and you'll find that the can gets crushed. Now, we don't have a vacuum pump. If you don't have a vacuum pump, you can do this experiment even at home. Very simply, if you put a little bit of water in the can and heat it until it turns into steam. Now, the steam is going to drive all the air out. Okay, as the steam is coming out, it has driven all the air out. You put the cap on. If you put the cap on and seal it tightly, then put it under the cold tap. The steam will condense back into water, leaving a vacuum here. Now, when inside there is a vacuum, you'll find that the air pressure squeezes the can and it crushes into this kind of shape. Now, here the can didn't get crushed because it was open to the air, and there's air inside it which is also exerting the same amount of pressure as the outside. Okay, so here it doesn't get crushed, but because there is no air inside, okay, there's a vacuum in here. That's vacuum. So there are no air molecules pushing on the outside from the inside. Therefore, the outside pressure crushes the can, and that's a very, very large pressure. Okay, and we're going to work that out. Another experiment that you can research yourself on Google. If you Google it, Magberg hemisphere, okay, and you'll find how strong the atmospheric pressure is. Now, we're going to talk about the mercury barometer, okay? It's an instrument that we use for measuring the atmospheric pressure. Now, how do we make a mercury barometer? If you take a very tall tube, about 1 meter long, more than 1 meter long. Now, you fill it up with mercury, okay? So we fill the tube up with mercury. Then you put your hand on the top of the tube and then turn it upside down into the trough of mercury. Okay, so that no air gets into it. Okay, so you'll have a vacuum in here. Now, when there's no air, you'll find that the outside pressure, which is pressing down on mercury, okay, it pushes the mercury up to a certain level. So and we find that H is equal to 76 centimeter of mercury. Hg stands for mercury. 76 or 760 millimeter of mercury. In other words, the atmospheric pressure is strong enough to support a column of 76 centimeter of mercury. Okay, now we want to work this pressure out in newtons per square meter or in pascals. Now, from the previous video, when we talked about the pressure of a liquid, we wrote down the formula. Pressure is equal to H times rho times G. Now remember, rho is a Greek letter which stands for density. H rho G. H is the height, rho is the density, and G is gravity. Now, for mercury, rho equals 13,600. Okay, let me write it. Let me write it over here. Density rho equals of mercury. I'm going to write Hg for mercury, which is 13,600. This is in kilograms per meter cubed. Okay, the density of mercury is this. The height of the column, which the atmospheric pressure can hold, is 76 centimeters. We're going to convert that into meters, which is 0.76 meters. Okay, because remember we're using SI units. So pressure is going to be equal to the height. The atmospheric pressure can hold a column of mercury which is 0.76 meters high. So H is 0.76 times the density of mercury, which is 13,600 times gravity, and G is equal to 9.8 newtons per kilogram. Now, I'm going to use the exact value. Normally we approximate it to 10, but I'm going to use the exact value, okay, which will give us a more accurate reading, which is 9.8. And if you work that out, it comes to 101,293. 101,293 newtons per meter square, or we say Pascal. Remember Pascal or newtons per square meter? I wrote newtons per square meter here to show you. So we say that the atmospheric pressure is approximately equal to 100,000 Newton on every square meter. Now, remember newtons per square meter. If I want to convert that into kilograms, if I divide this by 10, that is same as 10,000 kilogram. That's 10,000 kilograms per. No, it's like having a weight of 10,000 kilograms on every square meter, okay, which is 10 ton. The weight of 10 ton. If you imagine a big lorry. Now, if you take your dining table, for example, that has got roughly the area of 1 square meter. There's a weight of 10,000 kilogram acting on that. Okay, why doesn't the table get crushed? No, 10,000 kilogram, that's 10 ton, which is 10 metric ton of weight acting on that table. It's like a weight of a big lorry. If you can imagine that on your dining table, why doesn't the table collapse? There's so much pressure. Well, the reason is because the pressure, it doesn't only act from the top. The air can flow around and it can exert pressure from all sides. So like if this was the table, if this was your table, there's a pressure acting from the top, there's also pressure acting from the bottom. Okay, so which balances, okay, and from the side. So there's no net pressure. No, the atmospheric pressure is very large. Now, why don't we use this barometer out of water? Now, if we, instead of using mercury, the mercury is a very dense liquid. Its density is 13,600. That's about 13.6 times heavier than water. Now, if we used water, you can work this out using this formula. The height for the water, if you use the density as 1,000 kilograms per cubic meter, it comes to the height of about 10 meters, which is the height of nearly the height of a 3-story building. So you need a very, very long tube if you wanted to use water to make a barometer. Now, there are certain effects that happens with the atmospheric pressure. Like, for example, when you drink with a straw. Now, drinking with a straw, I'm going to rub this out. No, if you got a straw in here, okay. No, you suck on the straw and you take the air out. No, we think that, you know, when you drink with a straw, you suck the liquid up. You don't. Actually, it's the atmospheric pressure that pushes the liquid up. All you are doing is you're sucking the air out of the straw. So when the air comes out of the straw, that leaves a vacuum, okay? And it's the atmospheric pressure. It's the atmospheric pressure that pushes the liquid up, or the water or whatever juice you're drinking. It pushes it up, and that's how you drink it. It's the atmospheric pressure. We know that when you are flying in an airplane, the cabins of the airplane is pressurized. Okay, well, why is the cabin of an airplane pressurized? Because as we fly at a height, the pressure becomes less. So because people are used to the normal atmospheric pressure, okay, they're gonna get ill effects, okay, if the pressure is too low. So in order for the comfort of the passengers, the cabin is pressurized so that the pressure is kept the same as the atmospheric pressure. Why do astronauts wear spacesuits? Because they go into a vacuum of space where there's no air, and therefore the air pressure is kept normal inside the suit for their comfort. Okay. Otherwise, no. What happens if he takes his suit off? The astronauts, the blood pressure inside is balanced by the pressure of the air outside. So if there's no outside pressure, his whole body could burst, okay, because of the higher blood pressure inside. So this concludes the video on atmospheric pressure.